Thanks.
This meeting is being publicly streamed.
Okay, so the topic what we are going to discuss today, that is your electromagnetism. Okay, electromagnetism. So in electromagnetism topic, what we have to learn or what we have to basically understand, that is Huda. Welcome. Okay, got it. So in that topic, in electromagnetism, what we have to discuss, we have to discuss some points which are very important for us, and those points are actually the points what we have discussed some of the points in our IGCS here, O levels. That is why I divide the electromagnetism into four parts rather, and these four parts are, first of all, I will say that we will talk about general discussion about electromagnetism, right? General electromagnetism, this is very short and smart topic. We will revise some of the points about electromagnetism. Okay, then the second discussion about the electromagnetism, which is basically the force of electromagnetism or force, electromagnetic forces, that is your electromagnetic forces. Okay, the third aspect of this is basically the electromagnetic induction. Okay, and the fourth one is basically the alternating current. Okay, so is it clear now why I told that I will be talking about alternating current? Because that is based on some of the capacitors and some topics. That is why it will be done in this way. Okay, is it clear to everyone? Okay, so this is basically, these are the four parts of this electromagnetism. So first of all, when I will be talking about general electromagnetism, yani this is just a revision, I can say that some revision based on your electromagnetism. Okay, so first of all, whenever there will be a current carrying wire or any current carrying mechanism, what will happen? That will have an associated magnetic field, isn't it? So the topic starts right from here, that every current carrying conductor has an associated magnetic field, isn't it? That is the origin of your electromagnetism, that when a current flows through a wire, any wire, the electrons are disturbed basically, and there is a magnetic field developed across that. So when a current flows through a wire, through a wire or any conductor, what happens? A magnetic field is developed around it. Got it? Magnetic field is developed, okay, around it. This is the starting point. That is why I'm just writing in detail. So that magnetic field has some important characteristics, and that magnetic field can be, that is the current dependent. So we simply say that this is, that magnetic field is current dependent. That is why this topic is named as electromagnetism, right? So magnetic field, our magnetic field strength rather, that is what, that is current dependent. Mainly it depends upon current. So that is why This entire topic is called your electromagnetism. Is this clear to everyone? Or in the other way around, this is another fact, that when a conductor is placed in a magnetic field, a current is induced in the current in that conductor, right? So when a conductor is must conductor is placed, rather moved, in a magnetic field, then what did you observe? A current is induced in it. So that means that induced in it, and it shows this these two facts what you people have learned in your previous classes, that shows that current or electricity has an association with magnetism, and in the same way magnetism has an association with electricity, or rather I can say current. Instead of current, I will simply say electricity. Is this clear to everyone? That is why this entire topic is named as electromagnetism. This was basically the introductory uh, statements about the electromagnetism. So when I divide the electromagnetism further, electromagnetism is divided into three categories, but I will divide that into two just for revision. The magnetic field around a straight wire. Is it? Magnetic field around a straight wire. How many of you are aware of this entire discussion, that an if I have a wire with certain current, and that wire is placed in a magnetic field, let's say this is a copper wire. What happens? Just a second. Okay, just give me a second. I have to open the files again because I think it was having a problem. It was hanging up. Yes. Now it is visible to everyone. Same problem. Anyhow, let's say if we have a wire and that wire is placed in a magnetic field, let's say, oh yes, now it is done. So let's say we have a copper wire, and that copper wire is placed, a current is flowing through this wire, and the direction of the current is somehow upward. Let's say, what is the direction of the current? The current is flowing upward this way, right? This is the direction of the current. So do you people, now that there would be an associated magnetic field lines would be around this coil in a circular path in this way. Is it right? So let's say they were the circular paths, although it is not exactly the circular path, but these magnetic field lines will appear circular. Is it? And you people knew that these all magnetic field lines will be basically concentric, isn't it? Am I right? The magnetic field lines will be concentric, is it? So concentric means these magnetic field lines will have, uh, for example, if the current is out of the page, this dot will be there, and if you have the current into the page, there will be a cross, and around that cross you will have the magnetic field lines in the circular patterns, and these circular patterns will have a specific direction, and that direction will be shown to you here, right here. For example, if I say that in these red circles the current is out of the page, so the magnetic field lines will be, or magnetic field will be anti-clockwise, and if that is into the page, so the magnetic field lines will be clockwise. So I believe that everyone would be agreed with that, because you people have studied this all concept in detail in your previous levels. Okay, is it clear to everyone? Right? So this is not a big deal. But the only thing what you have to remember now, that here is the game of magnetic flux density, right? Magnetic flux density. Magnetic flux density. That is a term, new term, and that is included over here in our A levels. I will talk about that in detail. Uh, After some time, as well as right here I'm just going to tell you about magnetic flux density is represented by B. Its unit is Tesla. I mean, it is represented by T. And this magnetic flux, I'm not going to define magnetic flux density. Actually, it is magnetic field strength. It is magnetic field strength, right? So that is the same thing, because you people are already mean aware of this word magnetic field strength, but not about the magnetic flux density. So they are the same thing. So here you people learned one thing, that magnetic field strength or magnetic flux density was directly proportional to the amount of the current. And one more thing you people have learned, that it was inversely proportional to the separation between the, yani distance from the line, yeah, distance from the wire. So for example, if you have a wire here, and you have the magnetic field strength around the wire, that would be stronger, but as you are moving away, the magnetic field circles were spreading out. That was showing that the field is getting weaker and weaker and weaker. So is this clear to everyone? Yes. So these are 2 points what you have already learned in your previous level, and this concentration of the field lines tells you about the strength of the field. Concentration of circles tells us about strength of the field. Is it clear to everyone? Strength of field. So that is what you have learned, and I believe that there is not a big deal to know about that. Yes, the field lines would be yani when you will reverse the direction of the current, the field would be reversed, etc., etc. I think there is not a big deal at this level for you people to understand that. Now, the next point what I had to learn from the previous discussion, that is the magnetic field around a solenoid or magnetic field of a solenoid. Okay, magnetic field of a solenoid or a wire. So basically, this is the second aspect what we have learned, that yes, if we have a wire or if we have a coil, and that coil is basically having n number of turns, then that coil will have an associated magnetic field, and the magnetic field lines will be in different format as that of compared to that of the straight line. So here the current is entering at this point and current is leaving at this point. So all these curves are basically in this way. Now if I say that the magnetic field lines are straight or parallel inside this, and these magnetic field lines are basically spreading out as you are moving out of the coil. This is again very simple concept. There is no calculations at all included till this point, but you people learned that according to Fleming's left hand rule, this was the north pole of this coil, this was the south pole of this coil, and magnetic field lines were basically from south to north inside. And if I completely draw this field line, the magnetic field lines will be from north to south. Is this clear to everyone? So here, if you remember, you people were studying that the magnetic flux density was directly proportional to current in the coil. Magnetic flux density or magnetic field strength was directly proportional to number of turns, and magnetic field strength was directly proportional to area of the coil, etc., etc. Is it clear to everyone? So this was all what you have learned, right? And one more thing, which is basically now I'm going to switch to your A levels. That is the first topic what I would like to announce, that is force of, yeah, magnetic forces, right? So the topic will be magnetic force. Magnetic force. So students, when I talk about magnetic force, it means that magnetic force means the combination of external magnetic force or external magnetic field with the magnetic field of a current carrying conductor. This topic is basically studied in this way, that in this topic what we are going to learn, that is the combination of external magnetic force or external magnetic field, external field, and field of current. Are you getting this point? There would be two magnetic field lines in this topic, and when both the magnetic field lines interact with each other, then the force is developed, right? So this is the main theme. I will explain this in detail. When two magnetic fields or two magnetic forces, rather I will say magnetic fields, interact with each other, interact with each other, then what happens? Then a resultant force appears. Okay, resultant force appears. So that is why now my topic will be divided into some main parts. The magnetic force topic, that magnetic force will be studied here. We will study the magnetic force in this way. The magnetic force will be studied under these circumstances. First of all, we will say that magnetic force on yeah, around a straight wire. Secondly, we will talk about on a charge in a wire, charge in a wire. Third, we will discuss about on a free charge. Okay, right? Is it clear? Fourth, a free charge, free charge particle. Sorry, here I will write charge particle. Free charge particle placed in electric and magnetic force, right? Electric and magnetic field. The fifth aspect of this topic is the applications of this all, are application areas. And in application areas, there are two further steps. One is velocity selectors, and the second one are basically the Hall's effect. Right? So out of these two, velocity selector leads you towards mass spectrometer. There are further other devices as well, but we will study about mass spectrometer, whereas from the Hall's effect, you will study about Hall's probe. This is what the learning outcomes of this first half electromagnetic forces. Is this clear to everyone? This outline is clear? Okay. So moving to that straight wire, if I just tell you that you have to follow two concepts here, the dot and the cross concepts. Dot and cross means something. Dot means current is out of the page. Whatever, either it is current or magnetic field, it does not matter. This is a wire, and in that wire, I have shown the current, or that current is basically out of the page. Okay, that current is out of the page, and if I have the same wire, and that wire is basically placed in such a way that here the current is into the page, so I will show that with the help of a dot. Is it clear to everyone? Sorry, with the help of a cross. So cross mean into the page. You have to remember this point, into the page. Or if this cross will be shown to you, it means that moving away from you, away from observer. Okay, and if dot is there, it means moving towards or out of the page, out of page, or moving towards observer. Okay, so these are 2 points what you have to take care. Now first of all, I will just consider a simple situation. If I have a wire, okay, this is a wire, and that wire is placed in in a in an electric field, sorry, in a magnetic field here, and the wire has the current out of the page. Where is the current in the wire? The current, sorry, the current in the wire is out of the page. Then what will happen around this wire? What will be the direction of magnetic field around this wire? I'm talking about its own magnetic field. Its own magnetic field is anti-clockwise, is it? Huda and every other student, are you people getting this point? Okay, is it clear? Okay, so for example, now there are two magnetic field lines of this wire, and here there is a permanent magnet which is placed closer to this wire with the north on this side.
Sorry, can you please repeat that? I was reconnecting.
Yes, I'm saying that yes, here there is a wire which is placed uh, behind this screen, and the wire is placed in such a way that current is out of the page. This is current out of the page. Okay. Yes, Huda. From where should I repeat? Yani from which point? Hello, Huda. Is
Sir,
it?
you were saying out of the page and then your voice was lagging.
Sorry. From where? Yes. From this page.
Yes, sir.
Okay,
That
I
came
was
across.
saying that dot will represent the current out of the page or magnetic field out of the page, whereas your cross will represent the current or the magnetic field into the page. Now, according to that concept, I have just plotted the points. This is another wire. In that wire, the current is the current is out of the page, sorry, into the page. Here is the current in this wire. The current is into the page, so I will show that with the help of a cross. Got it? Cross went into the page, and if I draw the magnetic field lines around this wire, these magnetic field lines will be in the circular pattern like this, but this circular pattern will be equal to, or this circular pattern will be how much? That circular pattern will be clockwise or anti-clockwise? Yes,
Anti-clockwise?
anti-clockwise. Are you getting this point? So they will be anti-clockwise. So if
Yes,
I simply say that they are anti-clockwise, now I will give them, sorry, cross means clockwise, not anti-clockwise. Sorry, this is clockwise. According to Fleming's right hand grip rule, I will point my thumb in the direction of current, and then the direction of the magnetic field would be followed by the direction of my curling of finger. Did you remember that rule or not? This is north here, and let's say there is a south. Yes, Sudha, beta, clear hai?
yes, sir.
Okay. Now I have a question. Basically, my question is, if I have the magnetic field lines of my permanent magnet, there are some magnetic field lines. Let's say one, let's say two, let's say three here, and three magnetic field lines here. One, two, and three magnetic field lines here, right? The same magnetic field lines are basically here around this, I mean, in this magnetic field pattern. One, Okay, this is the magnetic field line number one. Okay, then this is the magnetic field line number two. Then the magnetic field line number three. Then the magnetic field line number four. Then the magnetic field line number five. Okay, is it clear to everyone? Anji? Now, I have a
Yes.
question. The question is, if you see on the on figure one, let me call it figure one. On this figure, what about the red arrows and black arrows on yani behind beyond this half? This is the half midway. Okay, here on the midway, I have drawn a magnetic field pattern. So yes, can you people please tell me? Yes, can anybody tell me? What about the magnetic field patterns here? Here on this diagram. Did you notice that these two black arrows and three red arrows are opposite to each other? Is it? Is it now? And these three arrows and two black arrows are in the same direction. So if I just draw the magnetic field patterns around this wire, which is basically the wire with its cross sectional area, here this is the dot, and around that dot, if I just draw the magnetic field patterns, then did you notice that on the right side of that the magnetic field lines would be cancelled out, and on the left side the magnetic field lines would be they would be concentrated with each other? Is it this way? This will happen in this way. Okay, then this will happen on that side. Yani the magnetic field lines are getting concentrated, isn't it? Whereas on the other side, only one magnetic field line is there. Is it? Is it now? So when there is only one magnetic field line, it means that the magnetic field lines are more on this side, whereas only one magnetic field line is on that side. You can even consider it as a magnetic field line, no magnetic field line, let's say, or I can just consider it a dotted line because that is the red one. So I'm just going to make it dotted. Is it? So what would be the impact of these forces? Here on this half, there is more force. Is it? And on this side there is less force, so that is why this wire will have an impact towards this way. You got this point? So basically this is the direction of the force. Now Fleming made this thing very easy, quite easy. And if you see this diagram, on this diagram, what did you notice? On this one, where the current is out of the page, where the field lines are cancelling out and where the field lines are in the same direction. So the field lines are basically in the same direction here, isn't it? They are in the same direction, black plus blue. But on the other side, the magnetic field line is only one, which is basically the in the dotted form, dotted line, that is red one. Okay, you got notice that point or not? So what will happen to the magnetic field lines, or what will happen to the magnetic force? Isn't it in this direction? Is it? बेटा ये बात क्लियर है सबको? Yes. So basically, Fleming told you this all in very simple way. Fleming ने ये कहा कि the direction of magnetic force, I will quantify that, don't worry. Direction of force, field, and current is determined by Fleming's which rule? Yeah, left hand three finger rule. Okay. So according to that rule, your index finger, your middle finger, and thumb. These are the three fingers, and these three will be perpendicular to each other, mutually perpendicular to each other. Index finger will show the field, middle finger will show the current, and thumb will show the force. Is this clear to everyone? So field, direction of field is usually represented by B. Direction of current or current is usually represented by I, and force is represented by F. Okay, so most commonly, this rule is called FBI rule. Although it is not FBI rule, but force, current, and magnetic field strength. So if I apply directly Fleming's left hand rule, so can I make it possible here? Where will be the direction of the force on this wire according to Fleming's left hand rule, three finger rule? Will it be in this direction? Yes. And will it be in this direction? Yes. Are you students? Is it clear to everyone? देखो, apply the rule. Point your left hand index finger in the direction of red arrows. Point your middle finger towards you. And where is your thumb pointing? For I'm talking about diagram number 1, figure 1. This thing. Point your index finger here in this direction. Point your middle finger towards your eyes. Where is the thumb pointing? The thumb is pointing this way, isn't it? So thumb shows the direction of force. And now on the second one, what do you have to do? You have to point your index finger downward. Then you have to figure out your middle finger inward, and your thumb is pointing this way, isn't it? Is this clear to everyone? Okay. So this was basically that aspect which was considered by Fleming's left hand rule. Now I will just quantify this force in few minutes, and then I will just wind up that it's quantification of magnetic force. When you quantify something, you need some physical uh, variables. So this force is directly proportional to current in the wire. This force is directly proportional to the magnetic field strength of the external magnet, right? Yani this I is what? Current in the wire. Yani in other words, magnetic field of the wire. Is it? And B is ex- magnetic field strength of external magnet of external magnet. Is it clear to everyone? So if we say that, yes, one more thing, that is that the force is also directly proportional to the angle or sine of angle between the wire and the magnetic field strength. So that is why if you just put all these together, that is equals to b I sine theta. And if I say that if this is removed, then we can apply a constant that is equals to bi sine theta. And if the length of the wire segment is kept constant, then it is equals to L is the constant. So bi sine theta will be used. So final equation for this is very common equation, that F is equals to B I L sine theta. You have to remember this equation, B I L sine theta. This is your first equation of your electromagnetism, what you have to recall and what you have to remember. Is it clear to everyone? B Bill sine theta, where if I just give you a simple visual of this concept, then I will simply say that, for example, if I have the magnetic field, and that magnetic field is in such a way that you have, yeah, these all are, this is the magnetic field, and there is a wire placed in a magnetic field whose length is L. Okay, this is a wire. Sorry, this wire is very thick wire. It's the wire has the magnetic field. Uh, yeah, this is a wire whose length is L. Now, what will happen? The current in the wire is, let's say, in this direction. What is the current in this wire? In this direction. So where will be the force acting on this wire? You will point the index finger into the page, your middle finger to the right, and where will be the force? Yes, here will be the force. Okay, is it clear to everyone? This is the force acting on this
Yes.
wire, and this is the current in the wire. So guys, simple and straight away, that if I have the length of this segment L, this is the length of this segment, and this is the magnetic field strength. So if we have an angle between the magnetic field strength, yani this is basically the B, and this is the length of the wire. If we have the angle between the magnetic field strength and the wire, so that angles matters a lot. So this is that angle. What is that angle? This is your angle theta, where let's say this is magnetic field, this is I, length of the wire or current flowing through that, because current is definitely acting on the wire, length of the wire. So force will be maximum when theta is 90 degree. So sine in 90 is 1. So for maximum force, one of the factor is that wire is placed perpendicular to the magnetic field. For maximum force, what is the prime factor? The theta must be equals to 90 degree. So that is why that force will be equals to B I L. So from this equation, I can simply define B, the magnetic flux density. And this is the defining equation for your magnetic flux density. That equation tells you that what will be B then. B will be equals to force per unit length of a wire if it carries unit ampere current. F divided by IL, or if divided by LI, whatever you think, but that is mean that it is Newton per meter per ampere, which is equals to Tesla. So if I want to ask you to define Tesla, so Tesla is Newton per meter per ampere. Okay, it is very common unit. So the magnetic flux density is defined as magnetic flux density B it is exam definition is the force per unit length of a wire normal to the magnetic field normal to the magnetic field due to unit current through that unit current through the wire through it. Is it clear to everyone? This is exam definition. Clear?
Yes. Yes, sir.
Yes. So till this point, we have Alhamdulillah completed this the magnetic flux density type thing. Then tomorrow, inshallah, we will discuss about the force on a wire, sorry, force on a charge, and hopefully on a free charge particle. And then the topic would be just quickly wind up. Okay. Any question you people want to ask me?
No, sir.
Okay. Yeah. No question at all. Okay. See you then. Allah Hafiz.
Hafiz, sir.
Allah Hafiz. Allah Hafiz.
Life is safe.
Allah Hafiz, Huda.